Hello and welcome to 4.4, which we're going to be dealing with limits again and something called indeterminate forms. And we're going to be looking at a rule called L'Hopital's rule. Now, before you start today's lesson, I'm hoping that you did the 4.4 review lesson and went back to chapter 2 if necessary to refresh yourself on limits as x approaches infinity, because you will need that knowledge for today's stuff. So just a reminder, if you have the limit as x approaches infinity of something like 3x squared minus 1 over 2x squared plus 1, there was a method where we could simplify this by multiplying the top and the bottom by 1 over x squared. That would give us something like 3 minus 1 over x squared all over 2 plus 1 over x squared. And as x gets very, very large, this term and this term will approach 0. And this leaves us with just 3 over 2. Now again, as mentioned in the review lesson, we did have a shortcut method, which was noticing that these are going to behave like the highest power you see on the top and the bottom. The highest power here being 3x squared on the top and 2x squared on the bottom. What will happen is the one on the top and the one on the bottom don't matter very much after x approaches infinity. So this is going to behave the same as 3x squared over 2x squared. Now x squared and x squared would cancel out here, and this would give me the limit as x approaches infinity of 3 over 2, which is 3 over 2. Either method is fine with me, but again, if you're taking an official calculus course at post-secondary, they may expect you to do this other first method here, multiplying by 1 over x squared over 1 over x squared. Now, the indeterminate form can be rewritten using various algebraic techniques. So when I plug infinity in, what I really get is infinity over infinity, but that doesn't really work. Okay. Now, all indeterminate forms can not be evaluated by algebraic manipulation like what we just did. There's going to be some functions where we can't do something like this. We don't have polynomials that we can simply simplify. This is particularly true when we have both algebraic, like what we saw, and transcendental functions involved. A transcendental function is a non-algebraic function, something like a logarithmic, exponential, or trigonometric functions. We can't simplify those using this polynomial method that we just used. For example, if I want to evaluate this guy, if I direct substitute 0 in, I get e to the 0 minus 1 over 0. E to the 0 is 1, so I get 1 minus 1 over 0, which is 0 over 0. Now we know from our limit chapters, we should be able to do something to manipulate this. Some of our stuff in our limit chapters was things like factoring and simplifying that way, or multiplying by a conjugate. Okay, now we can't do that here. So we're going to introduce a theorem called L'Hopital's rule. Okay? L'Hopital's rule says that we can take this limit as x approaches 0 of e to the 2x minus 1 over x and rewrite this as the limit as x approaches 0 of the derivative of e to the 2x minus 1 over the derivative of x. In other words, we're going to form a new limit by taking the derivative of the top and making that my new top, and taking the derivative of the bottom and making that my new bottom. And then we're going to see if we can direct substitute there. So if I do the limit as x approaches 0, and I do the derivative of the top, the derivative of e to the 2x minus 1 would be e to the 2x times 2. The derivative of 1 is 0. And on the bottom, the derivative of x is just 1. Now, if you'd like to rewrite this, you can, but essentially I get the limit as x approaches 0 of 2e to the 2x. Now I can direct substitute in here and get 2e to the 2 times 0 all over 1, which we don't necessarily need, which gives me 2 times 1, which gives me 2. And there you go. I was able to find a new way to evaluate this, even though I had an indeterminate form when I first direct substituted in. Okay. So what L'Hopital's rule says is if the limit of f over g results in the indeterminate form 0 over 0 or infinity over infinity, we can rewrite our limit as the limit of f prime over g prime. Now, this only works if we're starting with the limit of some rational of some sort, okay? If it's not a rational, we cannot do L'Hopital's rule. We must rewrite it as a rational first, and then we can apply L'Hopital's rule, okay? Now, there's a couple different things that you might see here. For example, you might see infinity over infinity, or negative infinity over negative infinity, or you might have one positive and one negative infinity, but the key here is that there's different types of infinity over infinity, okay? Your limit might be x approaching a. You might be approaching from the right or the left. You might be approaching infinity or 0, okay? Any of those are okay, and L'Hopital's rule can be applied. However, if you do not have a fraction, you must rewrite it. So for example, if I have the limit as x approaches 0 of x squared times ln of x plus 1. Let's say that's what I want to find the limit of. I cannot use L'Hopital's rule here, but right now if I plug 0 in, I'm going to get 0 times 0, which is not allowed, okay? So there are a couple other indeterminate forms I will list for you here in a moment. Okay? So this one, if I want to rewrite this as a fraction so I can use L'Hopital's rule, I can write this as the limit as x approaches 0 of ln x plus 1 over 1 over x squared. Okay? And that's because if I divide by 1 over x squared, this is the same thing as multiplying by x squared. Those are the same. Now, the other indeterminate forms you might see, okay, you might see infinity minus infinity. You might see 0 times infinity. You might see 0 to the power of 0. You might see 1 to the power of infinity. You might see infinity to the power of 0. So there's a couple indeterminate forms you could end up seeing here, okay? So let's try one of the form infinity over infinity, okay? So again, if I substitute negative infinity in here, what's going to end up happening is I'm going to have infinity squared over e to the infinity, and infinity squared is just going to give me infinity, and e to the infinity is infinity, and so that doesn't work. Indeterminate form of infinity over infinity. Now, because I know L'Hopital's rule now, I can rewrite this as the limit as x approaches negative infinity of the derivative of the top over the derivative of the bottom. Now, once you get going, you probably won't write this step. You'll probably just go straight to actually finding the derivative. Now, when I do this, the derivative of the top gives me 2x. The derivative of the bottom is going to give me negative e to the negative x. Now, if I plug infinity over infinity in here, I'm going to get 2 times negative infinity over negative e to the infinity, which again is going to give me negative 2 times infinity over negative infinity. And again, I'm stuck. I'm back to my indeterminate form again, which means I'm going to apply L'Hopital's rule again. You can apply it as many times as you need to until you can direct substitute in. Now, there were a couple special limits I showed you in chapter 2 that I said, later this year, we'll learn how to do these without needing to memorize these. L'Hopital's rule is what shows that those are true, okay? So I'm gonna apply L'Hopital's rule again. So again, I'm gonna go limit as x approaches negative infinity. On the top, my derivative is 2. On the bottom, my derivative is negative e to the negative x, which will give me the limit as x approaches negative infinity of 2 over e to the negative x. Now if I plug in, I'm going to end up with 2 over e to the infinity. If I take 2 and I divide it by something very, very large, this is going to approach 0. Now, there's a couple fairly tricky types of problems you might see. And so just a few reminders here, okay? So one reminder, okay, from previous chapters is if you have y equals a to the x, then dy dx is equal to a to the x times ln a. A little new fact, if I have ln of the limit as x approaches a of f of x, this is equal to the limit as x approaches a of ln of f of x. And where this is going to possibly come in handy is there are some very tricky questions you might encounter, especially in your textbook. Things like the limit as x approaches 0 of 1 plus x to the power of 1 over x. If I ask you to find this, the problem is that you get, as x approaches 0, you get 1 to the power of infinity, okay, which is indeterminate. And so what I would suggest doing is saying, okay, well, this has to equal some value y. Now, I don't want this 1 over x in my exponent, and in order to bring that down, I would need to ln or log something, okay? So if I ln both sides, I'm going to have the limit as x approaches 0 of 1 plus x to the 1 over x equals ln y. My answer to the question is y. Then I can rewrite this as the limit as x approaches 0 of ln of 1 plus x to the 1 over x using this new fact here. Now this will let me bring that 1 over x down in front. So I'm going to have the limit as x approaches 0. Let's put this in brackets just to make it clear. Of 1 over x times ln of 1 plus x. And now this is the same as saying the limit as x approaches 0 of ln of 1 plus x over x. And if I do this, I get 0 over 0. So now I can apply L'Hopital's rule. Okay, so I would get the limit as x approaches 0, the derivative of ln of 1 plus x is 1 over 1 plus x times the derivative of the inside, which is just 1, all over the derivative of the bottom, which is 1. Now this is the same thing as limit as x approaches 0 of 1 over 1 plus x. Now when I do this, if I direct substitute in, I get 1 over 1 plus 0, which is 1. And this is still my ln y. Now I'm trying to find y. So if I have 1 equals ln y, this is the same thing as e to the 1 equals y, or my original limit is equal to e. So if I go back up to my original limit, this is equal to e. Okay. So there's lots of different ways you can use L'Hopital's rule to solve some very, very gross limit questions. It's a very handy rule. And you might need to do some sort of manipulation to try and get into some of those problems. So some of you might want to just stick with some of the more basic questions like this one, or like the first one we did up here, but others might be up for a challenge in trying some questions that look something like this as you're choosing questions out of the textbook to try. And that is all for this section.